Okay, yesterday we had kind of a sprint through what discrete event simulation is about and a key piece of that called the event list, which handles the way that time advances. And again, just as a reminder, the difference between what discrete event simulation does as it advances time and other approaches such as time step is that instead of having a fixed increment of time that just sort of clicks up, what discrete event simulation does with the next event logic is simply advance time to the next event. And at least as a first cut, we can associate events with what we're calling state transitions. So remember, state variables are quantities that change throughout a given replication of a simulation, or at least could change. In contrast to parameters, which are, quote, variables which do not change. And we'll see an example of this in our canonical example, the multiple server queue. Now, we're going to go through modeling that because we've only done the simplest version of a discrete event simulation model so far, namely the arrival process, which is, even as simple as it is actually quite a useful one, as it turns out, much more useful than a typical hello world program in a language. It's roughly the equivalent in the sense it's the simplest non-trivial discrete event simulation model. It has one state variable, one parameter which consists of a sequence of numbers, and one event. So today we're going to look at a slightly more complex example, and the multiple server queue is in some ways a canonical example in that it was the motivation in the early days for doing this kind of modeling. Have you encountered the multiple server queue in your other class? Have you had a class in, say, stochastic processes where they've talked about queuing? No? Okay, so.
I think we kind of roughly talked about it in our AI class.
Okay, yeah.
Literally hearing the word queuing.
Yeah.
Well, queuing it's a fancy word for waiting online. And as they say, never use a large word when a diminutive one will do. So, and the word queue is kind of an interesting one. It's simply the letter Q followed by 4 vowels waiting in line. So we'll look at what that is about, and then you will, one of the things that I discovered when I first encountered this was that it's all over the place. As soon as you see this, it's like everywhere. And then kind of more to what we're going to start delving into, we're going to perform a simulation by hand. You say, well, what is a simulation model? I mean, I hope that at least at some point you're maybe thinking of expanding beyond a preconceived idea that a simulation model is a computer program. That is probably what most people think of. And the thing is that that's not necessarily the case. A simulation model does not have to be a computer program, and we're going to actually demonstrate that today. Now, if you want some serious answers out of a complex simulation model, then you're probably going to want to do it on the computer. However, it's important to understand what the event list is doing. And hopefully, by doing this by hand, and I'm going to torture you at some point by making you do it by hand, you understand how the program, which will eventually be dealing with programs, is supposed to work. In other words, how do you know that a given simulation program is executing correctly? there's another dimension beyond just sort of the regular kind of programs that we were looking at in the Java class, in the sense that this event list adds an extra layer of complexity. And so the question is, it boils down to, in debugging a simulation program, you need to make sure that all of the events are happening correctly at the correct time, performing the correct state transitions, and scheduling the correct events. And how do you do that? Well, the way you do that is by understanding how the event list works and knowing what it should be producing. Because if you don't know what it should be producing, then you have no way of evaluating whether it's doing the right thing. So we'll get to that. Okay, so multiple server queue. This is something that you encounter on a daily basis, at least if you're doing anything. But the idea is that we have customers, and I put customers in quotes because this model can be applied to situations where the customers may not necessarily be literally customers. So in this particular model, we have a certain number of identical servers. And again, servers are in quotes because it may or may not be a literal server person. So for example, if you're a website, your customers might be somebody trying to access your site from the browser. And your server might be the number of logical processes you have going on that can handle that. Or your computer goes belly up and you call tech support. And when you call tech support, what do you get?
Your place in line.
Yeah, you get your call is so important to us, and we're as soon as an available person is for you, then we'll. That's once you get past the recorded thing of press 1 for wherever. Terribly frustrating, of course, but that's an example of a queue. I mean, when you're sitting there waiting, you have that queue. And then when the service completes, then you go to the next customer. So when that call center person is finished with them, then they hang up, and then if there's somebody in the line, they go and they take them. So conceptually, it looks something like this. I mean, here's another example. If you ever have lunch by the little food hut they had out by the library, I think they have 2 windows. But on a typical lunchtime, you come and there are people kind of waiting in line. I don't know about today with the rain and everything. But you come up, and if there's nobody there, you kind of go right up to the counter. And if somebody is there, you all just kind of nicely wait online. So that's the model. I mean, or at least that's the situation that we're going to be modeling with a multiple server queue. And it's called multiple server queue. The multiple is because we can have more than one server. Okay, so now how do we model this? The structure that I strongly recommend is to begin with the parameters. The parameters of your model typically will come directly from the situation. And in this class, that will be something that's provided. When you're kind of doing this for real, it's typically a negotiation between the modeler and the people who are interested in this. So for example, in one of the models that I'm working on for NavSup, they're interested in fill rates for certain inventory policies of their various items. And so the negotiation was over, okay, if that's one of the key measures among many others that they're interested in, then how can we model that in a way which captures at least the essence of what's going on? So in the multiple server queue model, one is a quantity which is comparable to what the arrival process had. Namely, we're going to treat the arrival of customers like they were an arrival process from yesterday. In other words, they're going to periodically come up and show up for service. And our parameter are going to be a whole sequence of times, which are the times between when they show up, not the times they actually show up, because that's going to be determined by the simulation, but the times in between. And how might we get something like this? Now, when we start implementing this will be generated by a random variate. We touched on random variates a little last time. You've probably encountered them in your stats class and other types of things. Typically, this is generated by a probability distribution which produces that sequence. A second parameter are going to be the sequence of service times. That is, how long does it, once you get to the counter, how long does it take to get that done? And that's a totally separate set of values, right? Is that pretty clear? So, and then the final parameter is just going to be the number of servers. Call that K, but it's like you can call it anything you want. So in this particular case, the word K is equal to 3. But in this model, now again, remember, all models are wrong, and so this is a stylized depiction of what this system is. So in this system, the servers never get tired, they never get a break, they never take a break. We're just going to have that. There are going to be that many, and they're going to be there forever. The customers are going to come in forever. Okay, that's the model. Okay, and in kind of the after action, as it were, the approach to modeling that I think turns out to be most useful is one in which you start with the simplest model that captures the essence of what you're trying to do, and then look at the assumptions and see what does or doesn't work. Okay, so these are the assumptions. Be explicit about the assumptions, and then you can kind of evaluate whether or not those assumptions are reasonable. Okay, so those are the parameters. These are quantities which are not going to change throughout the simulation. The main quantities that do change, and there are really kind of two, but there are three just because of what we're interested in. The first is how many customers are waiting in the queue. So right here, assuming this guy just is about to show up here, Q is equal to 3. Okay, so if we stop our system, when you look at it, we see the Q is equal to 3 because there are 3 in the queue, and then these guys haven't shown up yet, so we don't really see them. So that's our first state variable. And it's going to start off with 0 because we're going to assume that when we start our system, there's going to be nobody there. Be like, let's say if you're a bank, you open up at 9 in the morning, and there's nobody waiting in line yet. Maybe they're waiting outside or something, but that's sort of, we're not going to assume that. Okay, the second is, now we have K servers total, and our second state variable is going to be the number of available servers. So this is going to be how many servers are available that is not busy and that can serve a customer who shows up. So for example, if in that call, as they're doing the call center, if S is bigger than 0, that is, if a person at the other end is available, then you won't have to wait. You'll get them right away. And every now and then that happens. That happened to me the other day, where it's like I was about to wait, and then all of a sudden it rang and the person picked up. So it happens. Not very often, but it does. So in this particular case, S is 0 because all 3 servers are busy. Okay? And now just as a final quantity that we're often interested in, or just how many are in the system in total. The system in this case consists of the customers in the queue and the customers who are in service. And oftentimes we're interested in the measures that are associated with that. And it turns out that for that particular state variable, if we know the value of Q and S, we know what L is. So, and this is the expression. So this is how many are in the queue. Now remember, S is the number of available servers, K is the total number of servers, so the difference is how many are busy. And if you're busy, it means you're serving one customer. You only serve one customer at a time. Okay, so,
Professor,
yes.
moving on to the next state. So when we push to the next state, does that occur when someone's been done being serviced, or does when something adds to the queue?
Yes. Okay, yeah, so that, what you're getting out of the state, okay, we've defined our state variables, and it's important to do that first, because if we don't have state variables, then we don't know what the state changes are. Okay, so now that we've defined them, that's exactly the next question that should be asked. Okay, what causes them to change? So let's take a look at the variable Q. What causes the number in Q to change? Well, one is somebody shows up. And what happens to Q when somebody shows up? It goes up by 1. Okay, now the second thing that happens to Q is when somebody goes from the queue into service. And what happens to Q in that case? It goes down by 1. Okay, so those are events. So that's, again, this isn't rocket science, but it's fairly straightforward. So that's how we define our events. And actually, it's useful actually to start with the run event, because every model has a run event. And the run event is responsible for initializing its state transition initializes its state variables. So you can always write down the state transition once you defined our state variables. And defining the state variables includes its initial value. So these values in parentheses, so the initial value of Q is 0. That's part of the state variable definition. And the initial value of S is K. That is, we begin with all of our servers available. And that, again, that is part of the definition of the state variable, its initial value. The consequence of that is you can always write down the state transition for the run event once you define your state variables. And that's important because that helps you overcome the blank page syndrome. Again, when we are doing this, the most effective way to do this is with a pencil and paper and a big eraser. And if you're a pro, you can use a pen. And I sometimes use a pen, but then I have to wind up scratching out things, so then I go back to the pencil. The dilemma there is, you know what the blank page syndrome is. It's like you get that whether you're working literally with a piece of paper or with Word or something like that. Have you ever had to write a paper and you open up Word and you're staring at a blank sheet here and you're sort of sitting there for minutes or maybe hours trying, you write a little bit, you erase it, you think, okay, what do I write? What do I write? Same thing applies here. So a big part of what we're going to be doing here is creating these models from a description. So our description right now is the multiple server queue situation, and this is how we create the model, and the blank page syndrome comes up a lot. The run event at least lets you write down something, and so it's not a completely blank page. You can always write this down. So the run event, in this case, we will initialize, this is our state transition. So we set Q to 0 and S equal to K. Where do we get that? From our definition. And because L, our number in the system, is a function of these, we don't have to be explicit about that. And then you say, okay, well, what happens in terms of scheduling? So the run event needs to schedule at least one event. Otherwise, what will happen is the run event will occur and then it'll just end. So you need to schedule at least one event. So what should we schedule? Well, let's schedule the first arrival with a delay of our inter-arrival time. Okay, so that defines, in this case, the run event. We have a state transition, we've scheduled the next arrival, the first arrival. Now, to get back to the question that you raised, what is it that causes, we'll pick a state variable, Q, right? What causes Q to change? Well, the arrival of a customer. Let's call that event arrival. Now, that name is arbitrary. We can call it anything we want. The name doesn't, calling it an arrival doesn't make it an arrival. What makes it an arrival for our model is this state transition. In other words, by saying this event causes Q to go up by 1, conceptually, we are saying a customer arrives and there's one more in the queue than there was before. Now, and that's really all we're going to worry about. Okay. Now, the thing about events is it's also useful to make them as small as possible and as atomic as possible. In other words, let each event do their job. Okay. So the only job of this event is to increment Q and then schedule the right events depending on what happens. So if a server is available when you show up, what we're going to do is we're going to schedule another event that says, we're going to call it start service because that's a descriptive term. And so the condition is that if the server is available, then we're going to say, okay, we can go right into service from the queue. And we're going to call it a delay of 0, and we can kind of talk about what that's about in a bit. But basically, we're going to say we can sort of instantaneously get from the queue to the server. I mean, in practice, it may take, less than a second, depending on how close you are. And if we are in a situation where it takes a certain amount of time to get there, that would require a different model. And that's an assumption we can examine. And then in addition, just like with the arrival process, we're going to schedule the next guy who's going to come. So we're going to schedule an arrival after a delay of another inter-arrival time. Okay, and that's all the arrival event does. In other words, it's this guy showing up, and in this case, since S is 0, he can't go into service directly. But if S were bigger, if 1 were available, he'd be able to just, again, not immediately, well, I mean immediately in terms of a 0 delay, but not worrying about that. Just this event is only concerned with incrementing the queue, and it's this second event, the start service event, that is going to, as you mentioned before, cause Q to decrease by 1. But it also does something else to our state variable S, the number of available servers, because when a server begins service on a customer, then they're not available anymore. So this event would only be scheduled if S was bigger than 0. In other words, if a server were available. So by subtracting 1 from S, that can always be possible. If there's a mistake in our model and we forget to put that condition in, then we could be in a situation where S could go negative. And these models are just as stupid as computer programs because they will do exactly what we tell them to and not what we want them to. So if we forgot this condition, then we might find ourselves in a situation where S goes negative. And so what does it mean to have -1 available servers? I mean, that's meaningless. Okay, so that would be a mistake in the model. Okay, so the start service is, we finally get through to the guy in the call center. We're now not in the queue, so that's been decreased by 1. That guy is not available anymore because they're helping us. And then what happens? Well, now that we're in service, we say, well, how long is it going to take? Remember, our parameter called T sub S was the amount of time it takes to service that customer. And so after a delay of that, we're going to schedule another event. We're going to call it end service because that's a fairly descriptive one. And what does end service does? It simply says, oh, well, now that you've finished serving a customer, we now have an available server. So it's like, what happens when you finish service? Well, now there's somebody who's available. Then what is that server supposed to do? Well, check the queue. if there's somebody waiting, then you want to serve them. If there's nobody waiting, then you just sort of stay idle. You stay available. So how can we express that in the language of the model? If there are customers in the queue, that is, if Q is bigger than 0, then we will schedule another start service event with a delay of 0. Okay, so now a couple things. This seems like a lot of verbiage, and this is why in either tomorrow or the day after, we'll start talking about ways of describing this in a more visual and compelling way, and that's what are called event graphs, which you can read about if you want to read ahead. But this is this is a model. This is a simulation model in every sense of the word. Now, what we're going to do now is we are going to be the event list. And so we can simulate this system without writing a single line of code, which should make some of you happy. But not for too long, because we're going to be doing code. Don't worry. But it's not 100% necessary. So let's look at a simple example. So we have our multiple server queue. What happened to my mouse? Okay, so here let's look at some parameters. So let's K be 1 just for simplicity, and we'll set a number of values. So these are the inter-arrival times. So the first inter-arrival time is 2.1. The second, now these are the times between customers. So the time between the first and the second customer is 1.4, and the time between the second and third customer is 3.5. Our service times, we're going to say the time to serve the first customer, we'll make it 2.2, and the time to serve the second customer is 1.3. And again, in a simulation program, these would either be we could pre-specify these, but more generally, we're going to produce these by a random variate generator. And for our stopping rule, we're going to stop when the second customer has completed service, because we're doing this by hand, and I don't want to make it 1,000 or 10. That is, when we have 2 end service events is when that's going to happen. Okay, so now this is kind of a little tableau that I'm going to make you do at one point, and there are example of these. There's another example of this in the reading with slightly different numbers. But we always begin with our states undefined and a run list on event list at time 0. So at the beginning of the simulation, before anything has happened, the time, the event, the states are all undefined. But all we have on our event list is we have that run event occurring at time 0. That's what happens automatically. And again, that's analogous to when we run a Java program. The first thing it does is it looks for a main method and starts executing that main method. So this would be when the Java virtual machine has found the main method, but before it has begun executing it. And so this is when we're firing up the simulation, but we haven't really started anything yet. And so it always starts like this. There's always a run event at time 0. That's where we start. That's the main. Now, we execute the events by following the event list rule. And what's the event list rule? We find the earliest scheduled event. We advance time to that event, perform its state transition, and then schedule any events that it has. So we advance time to the next scheduled event, which is which is the run event at time 0. So this is doesn't have my, there it is, okay. Okay, so this is the state of things just immediately before this. And so we advance time to the next scheduled event, in this case 0. So advance, we can advance by 0. 0 is allowed. It's just negative is not allowed. That's going back in time. So our current event is now the run event. It is now time 0. And then we perform the state transitions. So what is the state transition? Well, Q is 0, and S is equal to K, and K in this case is 1. So Q is now 0, S is 1, and remember L, the number in the system is, we can form by this expression. And that's 0. So we plug K is 1, S is 1, Q is 0, so 1 minus 1 plus 0 is 0. Then we schedule the next event. So in this case, we take the first inter-arrival time, which is 2.1, and we schedule, the delay is 2.1, our current time is 0, and so we schedule it to occur at 0 plus 2.1, or 2.1. So that, and that's all we do. And I say that because there is the temptation to kind of peek ahead. And the idea is that if you just kind of mindlessly follow this, then you're going to be better than if you do too much thinking. Okay. And then now, this is our state of the state of the simulation now is that we have just executed the run event. The current time is 0. Q is 0, S is 0, is 1, L is 0, and the event list now has an arrival event scheduled at time 2.1. And now we turn the crank again. And now we want to execute the first arrival event. So we advance time to the next scheduled event. So we go from 0 all the way to 2.1. And this is how it's different. If this were, say, a time step simulation where say the time step was 0.1, we would go to 0.1. But then at time 0.1, nothing has changed. In fact, nothing has changed here until that next event. So we advance time, 2.1, the arrival event. We perform its state transition. So what is its state transition? Well, all it does is it increases Q by 1. This is the only thing that it does. It doesn't affect S at all. But in this case, it's going to affect the value of L because now L is 1 plus 1, 1 minus 1 plus 1, and that's equal to 1. And then next we schedule any events. If you remember, the arrival event could schedule 2 events. We have the next arrival event with a delay of 1.4, and so that would be 2.1 plus 1.4 or 3.5. That's what we have right here. And we schedule a start service with a delay of 0. Now, we have to make sure we check the condition. Is S bigger than 0? Last I checked, 1 is bigger than 0. So that condition is true. And so we schedule a start service with a delay of 0. So 2.1 plus 0 is 2.1. And now we have a start service event as well. So now the event list has 2 events on it. And notice that in this particular case, within an event, the order that you do them doesn't matter or shouldn't matter. In this particular case, we actually we scheduled the arrival event first and the start service event second. But that doesn't matter as far as the event list is concerned because it keeps its events in order by when they're scheduled, not by when we've actually scheduled them. So now, the state of the simulation is we have just completed the arrival event. Q is 1, S is 1, L is 1, and there are 2 events on the event list. Now, just kind of continuing, remember our service times were 2.2 and 1.3, so our next service time is 2.2. And so our start service event, okay, so what do? We look for just the first scheduled event, in this case start service. We advance time and remove just the start service event. So that event, all the events that have not been processed are still there. We don't just magically make them disappear. What does the start service event do? It subtracts 1 from Q, so Q goes from 1 to 0, S goes from 1 to 0, and L actually stays the same by plugging that in. And what does it do? It schedules the end service event now. Our service time is 2.2. Our current time is 2.1. So the end service event is scheduled to occur at time 4.3, and there it is. Again, we do exactly the same thing. Now, we look at the event list. What is the next scheduled event, the earliest scheduled event? It is the arrival event at time 3.5. So, where are we here? Okay, the second arrival event. What does that do? It performs the state transition. Q goes from 0 to 1. That's all it does. It schedules the next arrival event. Now it's now time 3.5. Its next inter-arrival time is 3.5. So we have an arrival event scheduled to take place at time 7. But now, see, the current value of S is 0. And because of that, we do not schedule a start service event. And logically, it's like the second guy showed up, could not enter service right away, so just kind of stuck there. Now let's look at the next event. Let's see, we were right here. The next event to occur is the end service event at time 4.3. So that becomes the current event. We advance time from 3.5 to 4.3. We perform its state transition. What does it do? It takes S and goes one more. So that goes from 0 to 1. In this case, the value of the number of L, the number in the system, that goes down by 1. Again, if you plug into the equation, you'll see that is what it is. And now the only event that it could schedule is based upon the value of Q. In this case, is Q bigger than 0? Again, last that I checked, 1 is bigger than 0. So it will schedule another start service with a delay of 0. And that's what we have here. So at this point, the state of our simulation is that Q is 1, S is 1, L is 1, and our event list has a start service at time 4.3 and an arrival at time 7. And then finally, our second start service event, okay, that was here. We schedule that. What does it do? It decreases Q by 1 and S by 1. So they go from 1 to 0. It schedules an end service event with the next service time, which was 1.3. So our next end service event is scheduled to be 5.6. And then finally, 5.6, our end service event occurs. What does it do? It increases S by 1. So S goes from 0 to 1. And in this case, Q is equal to 0, and so it does not schedule a start service event. And now we've had our second end service event, which means our simulation is now going to end. Okay, so now what has transpired here? What has transpired is that if we look at each of our state variables, we have created a state trajectory. That is, if we go back, and in fact, we have all the values here. If we look at Q, we see that Q, if we were to kind of graph this, we see that Q starts off at 0. At time 2.1, it kind of pops up to 1, but then pops immediately back down. At time 3.5, it goes up to 1 again, but then does not go back down to 0 until time 4.3. And then it stays there until the end. So if we were to look at the state trajectory for Q, we would see that we spent a little bit of time in a positive state. And that leads to the kinds of questions we can ask of this. So a natural question one might ask is, what is the average number of customers in the queue? I mean, if you're running this system, that's something that you might be interested in. You know, why? Because how many of you love waiting online? And nobody? Okay. So if I'm the manager of this facility, then, and I want my customers to be happy, then the less time they wait in the queue, the happier they'll be. And so one measure that I would be interested in is, what is the average number in the queue? Now, I mean, obviously, in a more serious model, we would of course have to run it for much longer to try to get something like that. But even in this short one, we can answer the question for this brief situation. But the question is, how do we? You've all had stats, right? You all know how to take the average. So would your stats way of taking the average be the right way to find the average number in the queue here?
No, because you can't have the partial value.
Yeah. So, well, how would you answer that here? How would you find, if the question is, for this amount of time, what is the average number of customers in the queue? And how would you do it?
Take the mean and then just floor it.
How would you take, how would you find the mean?
Amount of queues divided by the number of events.
Okay? Now,
Minus
and that's what you learned in your stats class. Now, as you may guess, that's not the way we are going to do it here. Why? Okay, what if instead of this, well, what if we asked the question at this time, kind of before we encountered this? At this time here, before that second one, what would you say the average number in the queue is, just intuitively? Okay, now intuitive, look at the system. How much time did anybody spend in the queue at this point? Nobody. So intuitively, the average number in the queue ought to be 0. But if we count this, here was a 1 there. So if we use our stats approach to computing the mean, we're going to get a value bigger than 0, which intuitively shouldn't be the case. Okay, here's another situation. Okay, suppose we have something very similar, but instead of that, we have this. If you apply the stats method of mean, you're going to get the same value for each of these, right? Intuitively, does that seem right? I mean, intuitively, it shouldn't seem right, because here there was somebody in the queue for a short amount of time, and here there was somebody in the queue for a long amount of time. So intuitively, shouldn't the average number in the queue be greater when it looks like this? Intuitively, no? I mean, in other words, if I have somebody waiting in the queue for 2 hours versus 1 hour, shouldn't shouldn't the average be bigger in the second case? Okay, but the quantity was still the same. It was just one, let's say 1 in this particular case. So the the lesson is that if we want an accurate measure of what this is telling us, we need to take into account the amount of time that these states are spending in each of these states. Intuitively, right? I mean, and how can we do that? Well, by taking an average in a different way. And the kind of average that we will take is by looking at the area under the curve and dividing it by the time. Because if we look at these two different situations, here if we look at the area under the curve here is going to be smaller than the area under the curve in the second case. Now, when I say use a term like area under the curve, that might bring up some flashbacks to calculus. Remember integrals, area under the curve, right? You know. And that can, in some of us, that can cause a little bit of panic, but not to worry. In a discrete event simulation context, remember that the state trajectories are always going to be piecewise constant. And that means that the area under the curve is never going to be more complex than the area of a rectangle. And so the area of a rectangle, while technically an integral, is something that we don't need calculus to compute. So that's the good news. So the bad news is we have to worry about areas under the curve. The good news is that all we have to worry about are areas of rectangles. Okay, so we're going to explore that a little bit more in the next class. But that is it for what I have to say today. Are there any questions about any of this?
There is no textbooks for this course?
It's the textbook is the PDF.
Oh, is it?
The
Okay.
PDF, that's the text, yeah.